Namaste. Now we study potential energy of a dipole in an external electric field. If we place a dipole in an external electric field, how much energy is stored in the region of electric field due to the dipole? That is known as potential energy of a dipole in an external electric field. Energy possessed by the dipole by virtue of its particular position in the electric field is called potential energy of a dipole. To derive the expression for potential energy of a dipole in an external electric field, we consider a dipole having charge minus q and plus q. Electric dipole moment is P, placed in the region of uniform electric field E. Why uniform electric field? Because the electric field lines are parallel and directed upwards. We are keeping electric dipole in such a way that the angle between dipole moment vector and the electric field vector is theta. We are keeping the electric dipole in such a way that it makes an angle theta with the direction of electric field. Now already we know when we keep this dipole in an electric field, it starts rotating. That rotating effect is called torque. Expression for torque is already we studied in the first chapter, that is electric charges and electric fields. Tau is equal to Pe sin theta, where P is electric dipole moment, E is electric field intensity, theta is the angle between direction of electric field and the dipole moment. So this rotating effect of electric dipole in the region of electric field is called torque. Now, small amount of work done in rotating the dipole through a small angle d theta against this torque. See, this torque is rotating the dipole in the region of electric field. Now, to rotate this in the opposite direction, small amount of work is done to rotate the dipole through a small angle d theta against the torque produced in the electric field. That work done is given by the formula dW is equal to tau into d theta. Why we used here tau into d theta? Because this is the rotational motion. In the first year we studied work done in case of rotational motion is torque into angular displacement. Torque into angular displacement. In case of linear motion, work done is nothing but force into displacement. In case of angular motion, force is replaced by torque. Linear displacement is replaced by angular displacement. So substitute the value of tau here. P is sin theta d theta. Total work done in rotating the dipole from orientation theta 1, that is initial angle theta 1 to the final angle theta 2 is given by, just you integrate this P sin theta d theta, integrate over theta 1 to theta 2 to get the total work done. Small amount of work done is dW in rotating the dipole about an angle d theta, small angle d theta. To get the total work done in rotating the dipole from initial orientation theta 1 to final orientation theta 2 against the torque is given by W is equal to theta 1 to theta 2 tau d theta. If you integrate sin theta, we know sin theta integration is minus cos theta. Upper limit is theta 2, lower limit is theta 1. After substituting the limits, we get W is equal to minus P cos theta 2 minus cos theta 1. This work done is stored as the potential energy of the dipole. This work done is stored as potential energy of the dipole. Suppose we take theta 1 as initial orientation as pi by 2 and the final orientation as theta, Then substitute theta 1 as pi by 2, theta 2 as theta in the above expression. We get u is equal to minus p cos theta minus cos pi by 2. Cos pi by 2 is 0. So minus p cos theta, or AB cos theta is nothing but A dot B. So minus P dot E. Potential energy is a scalar quantity which is the scalar product of two vector quantities, that is nothing but electric dipole moment and electric field. Thus, potential energy of a dipole is given by U is equal to minus dipole moment vector dot product electric field vector, or dot product of dipole moment vector and electric field vector gives scalar quantity called electrostatic potential energy of the dipole. Thank you.